Brothers, welcome to this Field Explainer. Today we're zeroing in on the absolute most critical 24 to 48 hour window of your operation, diagnosing and solving nitrogen and phosphorus deficiencies. Look, if you manage a wastewater treatment plant, you already know your biomass is the beating heart of the whole system. When that delicate balance slips, things go sideways, and they go sideways fast. So let's get right into how we tackle Incident 7 head-on and save your activated sludge.
I totally understand the stress of a looming compliance violation. To get you sorted, we're going to hit two main things today. First up, problem, diagnosis, and investigation. Then we'll hit the emergency action plans and checklists.
All right, part 1, problem, diagnosis, and investigation. Let's jump right into identifying this crisis out on the floor and figuring out exactly what's eating away at your biomass.
So, when Incident 7 hits, you are staring down a medium to severe biological process failure. Cellular synthesis just drops. Your mixed liquor suspended solids, or MLSS, literally stops growing. You might be standing over your aeration basins, scratching your head, wondering why your sludge age is tanking and nitrification is completely shot. Well, it's because your bacteria are starving. They simply don't have the building blocks they need to multiply.
Brothers, if you're walking the tanks and you spot pale yellow or light brown sludge instead of that rich, healthy chocolate brown we all want to see, or if you notice pinpoint flock, you're already in the danger zone. Are you seeing your COD removal drop by 10 to 30%? What about cloudy, dispersed water in the aerobic tank, or a super slow settling layer in your secondary clarifier? These are the undeniable physical red flags of nutrient starvation.
I need you to practically tattoo this golden ratio in your brain, 100 to 5 to 1. You absolutely must maintain a BOD to nitrogen to phosphorus ratio of 100 to 5 to 1 to keep that biomass thriving. It's just the fundamental math of biological wastewater treatment. If your carbon load suddenly skyrockets or your nitrogen and phosphorus levels plummet, that ratio shatters and your flock structure breaks down right along with it.
Now, before we just throw chemicals at the problem, we need to find the root cause. A lot of the time, this comes down to the specific flavor of industrial wastewater you're treating. For instance, if you're pulling from a sugar processing plant, a brewery, or a paper mill, your influent is going to be incredibly loaded with carbon, but severely starved of nitrogen and phosphorus right out of the gate.
This could be caused by a whole bunch of things. Maybe it's a broken urea pump, maybe it's a massive, sudden COD spike from a seasonal food processing run. Or, hey, it could even be upstream chemical coagulation, completely stripping out your dissolved phosphorus before it ever hits the biological tank. This right here is where your detective work starts. And listen, do not rule out lab errors. Sometimes your crew might just be running the math on unrepresentative samples. Okay, time to put your boots on. I need you to physically step out of the control room and onto the floor. You absolutely cannot solve Incident 7 just by staring at a screen. You have to get eyes on the actual equipment and your hands on fresh samples.
Here is your exact battle plan. Grab consecutive influence samples every 4 to 8 hours. Run your actual ratio calculations. Physically check the MLVSS on site. If that MLVSS to MLSS ratio drops below 0.65, yep, you've got a serious problem. Finally, get that sludge under a microscope at 100 to 400x magnification. You're hunting for missing extracellular polymers, a total lack of ciliates, and way too many free-floating bacteria.
And hey, don't forget the basics. Physically check your dosing pumps. Are they clogged? Are the flow rates actually calibrated? Are the chemical tanks just straight up empty? It sounds ridiculous, I know. But an empty urea tank is one of the most common culprits. Also, pull your operational data from the last 7 to 14 days. You need to pinpoint the exact moment the balance broke and see if it lines up with any upstream production changes.
All right, part 2, emergency action plans and checklists. Once we know exactly what nutrient is missing, we immediately pivot to emergency recovery mode to save the system over the next few hours.
Time is absolutely of the essence here if you want to avoid a massive permit violation at your outfall. I'm going to walk you through the very specific 0 to 4 hour emergency responses. We have to get these chemicals prepped, safely handled, and dosed with total accuracy.
So, if nitrogen is your missing link, you need to calculate your deficit and immediately dose a 10 to 20% urea solution straight into the mixing point right before the aerobic tank. Then, over the next 4 to 24 hours, you adjust that flow to lock back into your 1:10:5 to 1 ratio. Oh, and watch your pH closely. Urea can definitely cause a slight ammonia bump, so keep an eye on that. Now, if phosphorus is what's missing, your immediate move is a dose of DAP. that's diammonium phosphate, or a 5 to 10% diluted phosphoric acid. But here's the catch, and it's a big one. You have to monitor your output relentlessly. You need enough orthophosphate to feed the cells, sure, but if you overdose, you're going to cause downstream eutrophication and trigger a total phosphorus violation right at your discharge point.
What if you're starved of both? Well, you have to split your combined DAP and urea dose into 2 separate applications, spaced about 2 hours apart. Why? Because hitting them all at once can cause a massive osmotic shock that will just wipe out whatever surviving bacteria you have left. Give it 12 hours. If your sludge is still looking pale, bump that dose up by another 20%.
But wait, what if your deficiency isn't absolute? What if it's a relative starvation caused by a huge, sudden influx of carbon? Think about it. You might be dosing your nutrients perfectly normally, but if the factory suddenly dumps a massive load of product down the drain, your system goes straight into shock. Brothers, a massive COD spike from the factory is going to instantly dilute your existing NNP. It completely obliterates your ratio. To the untrained eye, it looks exactly like a nutrient failure, but really, it's an organic overload.
During one of these massive COD spikes, you have to recalculate your nutrient needs based on that newly inflated COD number. If it is a severe overload, divert that flow to an equalization tank immediately. Temporarily cut back on your sludge wasting to preserve whatever biomass you have, and monitor your dissolved oxygen like a hawk. Those bugs are going to consume mind-boggling amounts of oxygen as they gorge on that sudden carbon feast.
Okay, let's talk about another silent killer of your ratio. Actually, scratch that. It's not silent if you know where to look. It's the physiochemical treatment step happening right before your biological process. Sometimes the problem isn't the raw wastewater at all. It's what your own upstream chemical treatment is doing to it.
If you're using zinc, PAC, or lime, they might literally be precipitating out your dissolved phosphorus before it even reaches your bugs. Your orthophosphate will just plummet to near zero. If you see this, you must immediately inject DAP after the primary clarifier. Long-term, you're going to need to permanently redesign your dosing points, or maybe look into switching your upstream coagulant to ferric chloride, which plays a lot nicer with phosphorus at high pH levels.
So, we've gone through the math, we've talked about the visual symptoms, and we've mapped out the specific emergency action plans. Now, let's consolidate the whole shebang into a practical tool you can hold in your hand on the floor right now. We want to make absolutely sure nothing falls through the cracks in the heat of the moment.
As a wastewater treatment plant manager or a shift leader, your success totally comes down to the disciplined execution of these recovery protocols over the next few crucial hours. Knowing the theory is great, but executing the plan is what actually saves the plant.
We've laid out your definitive field checklist. Look, do not clock out and leave the site until you have ticked off every single box on this list. From physically checking the chemical tanks and verifying pump calibration, to looking for dispersed growth under the microscope, to running those 4-hour and 8-hour SV30 follow-ups. Documentation and follow-through are not optional here. They are mandatory.
You now have the exact explainer manual you need to fix Incident 7. You know exactly what to look for, you know the math inside and out, and you have your emergency checklist ready to go. But I'm going to leave you with this final thought, brothers. Are your automatic dosing pumps properly calibrated today to prevent this exact nightmare from happening tomorrow? Stay proactive out there, keep those ratios tight, and protect your biomass.